Hello, good evening, everyone. I'm Akash Jyoti Pathak, and I welcome you all to the week two of this NPTEL course NMR Spectroscopy for Chemists and Biologists. I hope I am audible. So we will wait for 5 minutes and then we can start today's problem solving session. I am Akash Jyoti Pathak, and I am a PhD scholar in the Department of Biosciences and Bioengineering at IIT Bombay. And I am working in an NMR spectroscopy lab. So I am the PMRF TA of this course, and I will help you with whatever doubts you have regarding this course, and also I will we will together we will solve a few questions that will help you solve your assignments of week two. So I hope everyone has gone through the week two lectures. So if you have any doubt, you can ask. So we will start in another 3 to 5 minutes so that other people can join. So I will start sharing my screen. Yeah, so I hope everyone has gone through the week two lectures, and so we will understand all the concepts that were discussed in week two through a few sample questions. These questions will also help you in solving your assignment. So the first question is, out of the following, which sample will give the will give a high resolution NMR spectra? And we have four options over here: solid state, liquid state, gaseous state. All three states will give the same resolution. So I will give you 2 to 3 minutes to think, and then I will discuss the answer. So if any one of you know the answer, you can unmute yourself and tell, or you can also put it in the chat section. Tell your answer in the chat section. So one hint to this question is mostly when we record NMR spectra, the most commonly used state. Uh, I hope if anyone has ever Yeah, so mostly if we are considering the protein sample, they are usually in liquid state, and so our protein is in a buffer, and we load the sample in the NMR tubes, and so the most commonly used state for recording of a sample for recording NMR spectra is the liquid state. And why is it so? Because of a very obvious reason, that it is because liquid state gives us the highest resolution of NMR spectra. And what is the reason behind why liquid state gives us a high resolution NMR spectra? So yes, the answer is option two. And in liquid state, what happens is the nuclear spins show very fast molecular tumbling, and because of this molecular tumbling, we get sharp lines resulting in high resolution NMR spectra. Right. And then what happens in solid state? In solid state, the nuclear spins are very close to each other. And because of this closeness, we get very broad and overlapping peaks. The peaks are not sharp. And also in the solid state, in solid state, you can consider that our protein sample, or whatever be the sample, it is in a powder state. So because of this, there is very less tumbling, and hence almost there is no tumbling, and hence we get broad and overlapping peaks. And in gaseous state, the spins are very far apart, and they have very low signal intensities due to low number of spins. So the correct option for this question is liquid state. Liquid state sample will give the high will give a high resolution of NMR spectra. Yeah. Moving to the second question. So in the second question, in an NMR spectrometer of 500 megahertz, two peaks are present at 2.3 ppm and 1.8 ppm. What would be their peak separation in terms of hertz? Then there is a second part to this question, that in a 800 megahertz spectrometer, this peak separation would correspond to. So here you need to apply the concept of how you can convert ppm into frequency, that is in hertz. So there is a very simple relation by which you can convert the ppm into hertz, and this concept was described in lecture 5. This was described how we can convert the ppm into hertz. So I would give you 3 to 5 minutes to think, and then we will solve this question. So these type of questions are also there in your assignment in week 2. So understanding the concept is very important. So why do we get different peaks or different lines in an NMR spectra? What is the concept behind it? So I had discussed these concepts in week 1. So what happens is there are different nuclei in a sample, and each of these nuclei has a particular resonance frequency. And so what happens in an NMR spectra? In an NMR spectrometer is first the sample is placed in the sample in a sample. There are different nuclear spins, so they will have the same energy level and they will be randomly oriented. Now when this sample is placed in a strong magnetic field, the nuclei will there will be splitting of the energy state, right? And depending on the depending on the type on the nuclei, what type of nuclei is present, with whether it is a proton nuclei or a C13 nuclei, the we will get there will be different separation in the energy states. And also we had discussed about the gyromagnetic ratio, that the gyromagnetic ratio plays an important role in the energy separation between the energy state. And now when a radio frequency energy is applied to the sample, there will be the nuclear spin will move from one energy state to another energy state, and this move the energy that they will absorb will be that energy that they absorb. We can see that in a NMR spectra. So in NMR spectra, we have the frequency on the x-axis, and the intensity of energy absorption is on the y-axis. So I hope you remember the formula for chemical shift. So chemical shift delta is given by nu minus nu naught by nu of the frequency of the spectrometer into 10 to the power 6, right? So delta, what is delta over here? Delta is called the chemical shift. Delta is called the chemical shift. And then the chemical. So in this question, the chemical that we get two peaks. One is at 2.3 ppm and another is at 1.8 ppm. So the separation between these two peaks is how much? 2.3 minus 1.8. 2.3 minus 1.8 ppm is the separation between the two NMR peaks. And now what you have been asked to find here is you have to calculate the peak separation in terms of hertz. That is, you have to calculate this value, nu minus, or nu1 minus nu2 also you can consider. So there are, for example, there are two nuclei. One has a frequency resonance or the chemical shift of one nuclei is will be in is nu1 and another will be in nu2. Okay, so or we can say that the resonance. Uh, just a second. Yeah. So nu1 is the resonance frequency of one nuclei and nu2 is the resonance frequency of another nuclei. And what is the frequency of the spectrometer? It is how much? It is 500 megahertz, right? 500 megahertz. That's megahertz. Now, if you have to calculate the value of nu1 minus nu2. So how much will it be? It is 0.5 ppm, right? And it is 500 megahertz. 500 megahertz divided by 10 to the power 6. So what we will get if we solve this? So 500 megahertz means 500 into 10 to the power 6 hertz.
0.025.
Yeah, 2.3 minus 1.8. I hope this is correct. It is 0.5 ppm, right? 2.3 minus 1.8 ppm is 0.5 ppm. So this will cancel.
250 hertz.
Yeah, so we will get 250 hertz. Right. So this is so if we want to convert the value of frequency from ppm to megahertz, then we can directly use this formula for chemical shift, delta equal to nu minus nu naught by the divided by the frequency of the spectrometer into 10 to the power 6. Okay, and one more concept over here you can remember is that, so if you are, for example, if you are using a spectrometer of 500 megahertz, then 1 ppm would mean 500 hertz, right? So similarly, if you are using a spectrometer of 800 megahertz, then in a 800 megahertz spectrometer, 1 ppm would correspond to 800 hertz. Okay, so why is it so? So this is because what we have to calculate nu minus nu naught. Nu minus nu naught is what? Nu minus nu naught is equal to the chemical shift into nu frequency of the spectrometer into 10 to the power 6. Now the frequency of the spectrometer is always in megahertz. Sorry, into 10 to the power minus 6. right? So the frequency of the spectrometer is in is in terms of megahertz. So this one gets cancelled. 10 to the power 6 into 10 to the power minus 6, and so this one becomes nu minus nu naught becomes into so yeah. So we will have this new spectrometer, right? So nu minus yeah. Sorry. Just a second. Hmm. Just a second. Okay, so what I was saying that we have to if we have to calculate the separation of peaks in terms of frequency, then nu minus nu naught equal to del into chemical shift into the frequency of the spectrometer. So if this is 1 ppm, if this is 1 ppm, then 1 ppm would directly correspond to actually what I will do is I will write it once again so that because this has become. So you have to calculate nu1 minus nu2, and this will be equal to the chemical shift into the frequency of the spectrometer into 10 to the power 6. And just a second. So if the chemical shift is 1 ppm, if the chemical shift is 1 ppm, then this this separation in peak frequency would be directly proportional to the frequency of the spectrometer in hertz. This is in hertz because the frequency of the spectrometer will be in megahertz, and this is 10 to the power minus 6 when this will come. Yeah, this 10 to the power 6 will go to the denominator, and we will get this in when we will get this 10 to the power minus 6. So just remember that 1 ppm will be equal to the frequency of the spectrometer in hertz. So for example, so in this question, rather than applying this formula, you can directly solve it in this form also. So so yeah, I'll just show you the slide. So since the Yeah, so what I said just now is that always remember that if the reference frequency is 500 megahertz, then 1 ppm would correspond to 500 hertz. Now here the difference in chemical shift is difference in chemical shift is 0.5 ppm. Now 0.5, so if 1 ppm is equal to 500 megahertz, then 0.5 ppm would correspond to 250 hertz. So this is the so the answer of the first part is 250 hertz. It's 250 hertz. Now if you are using a spectrometer of 800 megahertz, what would be the peak separation? What the peak separation would be how much? So you can apply the similar concept here that 1 ppm for a 800 megahertz spectrometer, 1 ppm would be 800 hertz, right? So 0.5 ppm would be, so it will be how much? So it will be 400 hertz. So this is wrong. This will be 400 hertz, right? Yeah. So I will correct this question. This will be, the correct answer is option 3, and it will be not be 1600 hertz. It will be 400 hertz. It will be 400 hertz. So I hope everyone has got this question. So what is the concept of chemical shift? Does anyone remember?
The concept of chemical shift is the key. If we applied the frequency, then every molecule have a specific nuclei present in their orbital. Okay.
Yeah,
If the radio frequency applied, then according to their
resonance
molecular
frequency.
function or vibrational in bond, they will separate each other and give the intensity according to uh, their functional group present in the molecule.
Yeah, you are correct. So every nuclei has a particular resonance frequency, and depending on its resonance frequency, the energy, that the frequency of radiation that we apply, it will absorb it will absorb that energy, and we will get its character. We will get its chemical shift, right? Depending on what is the resonance frequency, or what is the alarmal frequency of that nuclei. Okay. So, for example, so this is the, so on this axis we have the frequency, and on y-axis we have the intensity of absorption. Okay. Now moving to the next question. So a proton has a chemical shift of 4.62 ppm relative to TMS. What is TMS? TMS is tetramethyl silane. It is a reference compound with respect to which, this is a reference compound. The chemical shift of all other nuclei are calculated with respect to this reference compound TMS. And so in this question, you have to find the chemical shift and resonance frequency of proton in hertz in a 500 megahertz instrument. So for this question, you have to assume that the TMS resonates exactly at 500 megahertz. So what is in this question? What is the question trying to say? So you are recording the NMR spectra, and you have got the chemical shift of the proton at 4.62 ppm. 4.62 ppm, and now you have to calculate. Okay. So you have got a So for example, this is the peak of proton, and this you have obtained this at 4.62 ppm, and so you have to report this ppm in terms of hertz. Right? So in terms of hertz, what will be the chemical hertz? What will the chemical shift? So you have to apply the same concept that we applied in the last question. You can take 2 to 3 minutes to solve this question, and then if you have got the answer, you can unmute yourself and tell the answer, or else we will solve. We will discuss the question after 2 3 minutes. So the chemical shift is always reported in ppm because why is it so? Because if we as we know that the resonance frequency is equal to gamma b naught. Now, this resonance frequency depends on the external magnetic field. So, depending on what type of NMR spectrometer we are using, for example, we are using a 250 megahertz spectrometer or 500 megahertz spectrometer, the resonance frequency will be different. So that would be a problem. For example, if someone in a particular country or in a particular institute is recording a spectra on a 500 megahertz spectrometer, and someone is recording the NMR spectra in a 800 megahertz spectrometer, they will have different frequency. So since this creates a problem, what we do is we calculate the frequency with respect to a reference compound, and the most commonly used reference compound is TMS, tetramethylsilane. So it is similar to. So you can think of this. You can take an analogy. So for example, you have two numbers like 6 and 2. So the difference between 6 and 2 is how much? It is 4. And for example, you have now we have two numbers. For example, 14 and 10. The difference is 4, so the difference will always come same, whether the numbers can be different, but the difference is same. So this is the concept of chemical shift, that chemical shift is measured with respect to a reference compound. So with respect to the reference compound, we will get the same chemical shift, whether the nuclei, whether the spec or the whether the spectra of the nuclei is recorded on for a 500 megahertz instrument or an 800 megahertz instrument. So for this question, so what I just said now, that 1 ppm will be equal to the will be equal to the frequency of the NMR spectrometer. So if it is 1 ppm, then 1 ppm would in a 500 megahertz instrument would correspond to 500 hertz. And you have recorded a chemical shift of 4.62 ppm. So 4.62 ppm would be equal to 500 into 4.62 hertz. So calculate this and tell me the answer. It is 2310 hertz. Always remember that always remember that 1 ppm would be equal to the frequency of the NMR spectrometer in hertz. Now, the second part of the question, the chemical resonance frequency of proton. What will be the resonance frequency of proton in hertz in a 500 megahertz instrument? So what will be the resonance frequency? So here you have been told to assume that the TMS, so you will get a peak of TMS at 0 ppm, right? So since it is a reference compound, so the reference compound has a, usually we take the reference compound has a chemical shift of 0 ppm. So since this TMS resonates at 500 megahertz, so this would mean that 0 ppm is how much? 500 megahertz. And how much is this one? This 4.62 ppm, we just now calculated that 4.62 ppm is equal to 2310 hertz, right? So the resonance frequency of the proton would be 500 into 10 to the power 6, which is how many zeros? Zeros. Plus 2310. So in hertz, this will be equal to 500,2310 hertz. Okay, so the correct answer is option 4. Yeah. So this is the solution. So in a 500 megahertz instrument, chemical shift of 4.62 ppm would be equal to 2310 hertz. Now, assuming that TMS resonates at 500 megahertz, the proton would be resonating at 500. So since we considered this 0 ppm, so this was 4.62 ppm. But if 0 ppm corresponds to 500 megahertz, right? Uh, so in terms of hertz, the proton would be resonating at 500 megahertz plus this 2310 hertz, which would be 500,002,310 hertz. So we will get these type of questions in your assignment. Moving to the next question. So in an NMR spectrum, a downfield chemical shift of nuclei X with respect to chemical shift of another nuclei Y would mean option 1 is nuclei X is shielded, nuclei X is deshielded, nuclei X has a higher ppm value than nuclei 1, and both 2 and 3. So you have a nuclei X. So what is the question asked over here? So you have a nuclei X and another nuclei, you have another nuclei which is Y. Now with respect to nuclei Y, with respect to nuclear Y, the nuclei X has a downfield chemical shift. So what would that mean? So this is an NMR spectra and you have two nuclei X and Y. You record their chemical shifts. This is, for example, 0 ppm. And then, so what does downfield chemical shift mean?
Nuclei is deshielded.
Nuclei would be what?
Deshielded.
Yeah, deshielded. What is meant by that the nuclei is deshielded? So downfield chemical shift of nuclei X with respect to chemical Y would mean that the nuclei, if this is 0 ppm, and here, so from left to right, the ppm, the value of ppm is increasing. So downfield chemical shift of nuclei X with respect to nuclei Y would mean that the nuclei X is in this position and nuclei Y is in this position. So downfield with respect to Y means that this This X is at a higher ppm, at a higher ppm value than nuclear Y, than nuclei Y. Okay. So de-shielded means that so we have nuclear spins, right? And the nuclei is surrounded by an electronic cloud. Okay, nuclei. So the nuclei is surrounded by an electronic cloud, and this nuclei is not in isolation. It is attached to another nuclei. Okay. So there may be another nuclei can be anything. It can be any electronegative atom, Cl, or it can be an oxygen atom. So depending on what type of atom you have, what type of nuclei you have, the what it does is that the nuclei will attract the electron cloud towards itself. Will attract the electron cloud towards itself, and this is what is meant by de-shielded. De-shielded is means that the electronic cloud surrounding the nuclei gets is shifted towards is shifted towards another nuclei, and because of this, what will happen? So we are applying a magnetic field V naught now. Now what happens is that since electrons are also charged, they will also have a magnetic field. Since the electrons are charged, they will also have a local magnetic field, and so this magnetic field they will have a local magnetic field. So, for example, B local, okay, and so we get a net magnetic field. So in presence of another nuclei, the nuclei, for example, this is X and this is Y, the nuclei will experience a net magnetic field. So So I hope you remember this formula that H local will be equal to H naught 1 minus sigma, right? So sigma is the shielding constant, and the H local is also, we can say that this is the net magnetic field, net magnetic field experienced by a nuclei. So the net magnetic field experienced by a nuclei will correspond to the chemical shift that it will show in an NMR spectra. Okay, so if an electronegative atom or the electron is shifted towards one particular nuclei, then it is said that the nuclei is de-shielded. While if the nuclei remains surrounded by an electron cloud, it would mean that the nuclei is shielded. Okay, so what happens whenever the nuclei is de-shielded? It shows a higher ppm value and shows a downfield chemical shift. This is downfield chemical shift. Okay, so the correct answer for this question is option 2 and option 3, both are correct here, and so the correct answer is option 4. Yeah, so nuclei X is de-shielded. Since nuclei X is de-shielded, so it will have a higher chemical shift or higher ppm value than nuclei Y. I hope this concept is clear. So sigma is called the shielding constant, you can say, or the screening constant. So more the screening. So if sigma is very high, then what will happen? Then H local will be less than H naught, right? And if the shielding the lower the shielding constant, then H local will be greater than H naught. So the more the shielding, it will there will be less chemical shift, and the lesser the shielding, or the more the de-shielded, the more will be the each local value, and hence you get a higher value of chemical shift. So moving to the next question, which of the following statements about chemical shifts are correct? So the first is the chemical shifts are measured in parts per million relative to an external standard. Second option, the chemical shifts are same for all type of NMR active nuclei. The third option is the chemical shift of a proton in an NMR spectrum is not affected by the electronegativity of neighboring atoms. And fourth option is chemical shifts are independent of the applied magnetic field strength. So read the statements and then you can answer the question. So go through the statements once again, and then you can tell me the answer.
I think option 4, chemical shift are independent of the applied magnetic field strength.
Okay. So one by one, we will see the statements. Yeah, option four, yeah, is option. First statement is chemical shifts are measured in parts per million relative to an external standard. So this statement, what about this statement? Is this a right, correct statement or wrong statement? So we know that the chemical shifts are measured with respect to a reference compound. Usually it is TMS or it is DSS. DSS is the reference compound for protein, and TMS is the reference compound. For example, if we have any organic compound or any inorganic compound, then the chemical shift of those is calculated with respect to TMS. But for protein, the reference compound is DSS. Then second, so this are measured in parts per million. So this statement is correct. Then option 2, chemical shift are same for all types of NMR active nuclei. Now this statement is false because different NMR active nuclei will have different resonance frequency, and they, depending on their resonance frequency, they will have they will show a particular chemical shift when placed in an external magnetic field. So this statement is wrong. The chemical shift of a proton in an NMR spectrum is not affected by the electronegativity of neighboring atoms. So just now we discussed the concept of shielding and what we had just said now, that each local is equal to H naught 1 minus sigma. So the chemical shift of a proton will depend on its surrounding environment. If the proton is surrounded by an electronegative atom, then the electronegative atom will attract the electron towards itself, and hence it will be its screening or the shielding will decrease, and so the chemical shift is affected by electronegativity. So the more the electronegativity, the higher the chemical shift, right? So you have seen in the lecture that chemical shift depends on several factors. So one of the factor is electronegativity. So the higher the electronegativity of the neighboring atom, the higher will be the chemical shift. And the fourth point is chemical shifts are independent of the applied magnetic field strength. Now this is all. This is false. The statement 3 is false, and chemical shifts are independent of the applied magnetic field strength. This is also false. So just now we had seen that in an 800 megahertz spectrometer, it will have a particular chemical shift. Okay. With respect to a reference compound, the chemical shift will be independent of applied magnetic field. So chemical shifts are independent of applied magnetic field with respect to a reference compound, right? So if this was the statement, then this question would be correct. So Guddu, do you understand why is this statement wrong? So the chemical shifts are independent of the applied magnetic field strength with respect to reference compound. But without any reference compound, when there is no, if you are not using any reference compound, then the chemical shift will depend on the strength of magnetic field, and that is what we were seeing in question number 1 and 2. So in 800 megahertz, it had a particular chemical shift. In 500 megahertz, it had a different chemical shift. So this statement is also wrong. So the correct statement is option one. So these are the, so yeah. So this is the formula for chemical shift. Delta ppm equal to nu minus nu reference. Nu reference is this is usually zero. So this is taken as 0 ppm. So nu reference is the frequency of the reference compound. Is the frequency of the reference compound. So the chemical shift of the reference compound is taken 0 ppm, but in terms of hertz, it will have a particular frequency. And nu naught, what is nu naught? Nu naught is the frequency of the spectrometer in which we are recording the NMR spectra. Okay, yeah, so whatever I discussed just now, those are written over here. So different. So this statement 2 is incorrect because different nuclei will have different resonance absorption frequencies, and hence they will have different chemical shifts. Now, why was the third statement wrong? Because the electronegativity of neighboring atoms will so depending on the electronegativity of the neighboring atoms, it will determine whether the electron cloud of the nuclei which we are considering, whether it will be surrounding the nuclei, or whether it will be attracted towards the electronegative atoms. So it will depend on electronegativity. And the third statement, that chemical shifts are independent of applied magnetic field strength. So this is also wrong. And chemical shift, so with respect to reference compound, this will be independent. But if we are not using a reference compound, then higher the magnetic field strength, the higher will be the chemical shift. Okay. So moving to question number 6, the number of peaks observed when NMR spectra of methyl acetate is recorded will be 4632. So how many peaks you will obtain in an NMR spectra? So it is so the concept of chemical shift is that it is not necessary that if it is H1 nuclei proton, for example, it is a proton nuclei, it will always have a particular chemical shift. The chemical shift of a particular nuclei will depend on the surrounding, depending on the nuclei by which it is surrounded. Okay, so it is so whether the proton is surrounded by other nuclei like fluorine F19, or whether it has any electronegative nuclei attached in its surrounding environment, or any methylene group. So these factors come into play when we are measuring the NMRs when we are recording the chemical shift of any nuclei. So whether it is not necessary that each one proton nuclei will always show the same chemical shift. So a different proton will have different chemical shifts depending on the surrounding environment, depending on what are the nuclei which is surrounding this proton, surrounding this proton. Okay. So I will give you a hint. The formula for methyl acetate is
Two.
CH3. Okay, we will see if it is 2 or not. CH3COO, CH3. So number of proton peaks. The question will be number of proton peaks, H1 peaks that you will observe. So I will allow others to think, and then I will discuss the question in 2 minutes. So this is the formula of methyl acetate, and you can see there are two different protons. One is the methyl proton over here, and another is the methyl proton, which is attached to a COO group or an oxygen atom. So what I was just explaining now is that this H has a different environment, is surrounded by a different environment than this proton. Okay, if you break this, so, so now you can think how many peaks you will observe for the compound methyl acetate. So the number of peaks that you will obtain will depend on how many protons are in different chemical environment. You can think it like in this manner that so we have so if there are the protons, but if they are in the same environment, they will have the same peak. But if there are protons which are in different environment in different which are surrounded by different nuclei, then they will have different peaks. Yeah, so the correct answer for this question is option number 4. So so if you consider the peak of TMS, if you consider the peak of TMS, then you will have three peaks, right? So TMS will also show a NMR peak. This will be at 0 ppm. But other than the TMS peak, if you do not consider the TMS peak, then you will get only two peaks. Okay, you will get two peaks. One is this for the proton. These protons. These protons are chemically equivalent because all these protons are attached to the carbon group, and in the surrounding of these protons we have this is attached to the carbon, and this carbon is bonded to another carbon. So these are equivalent protons, and these protons are bonded to carbon, and now this carbon is bonded to an oxygen atom. Because of because of the electronegativity of this oxygen nuclei, the electron clouds get shifted from these protons, and hence they will show a NMR peak at a different ppm value. Which one will be at a whether so for example, this is HA, and these are HB. So which will if you record the NMR spectra, then which one will show a higher chemical shift, HA or HB? So where will you get the peak of H and where will you get the peak of HB? So so for this question, actually it will be mentioned in the question that with That if the question is asked that number of peaks considering the peak of TMS, then the correct answer will be option 3. But if we do not consider the peak of the TMS, then the correct answer is option 2. So this is the peak of TMS, and then you will get another 2 peaks. Now you have to say that this peak will be of which proton, HA or HB, and this peak will be of which proton, HA or HB. So can anyone comment? Comment on this peak will be for which proton and this peak will be for which proton. So yeah, just now we discussed that the proton which remains attached to an electronegative atom is shows higher de-shielding, and hence if it is de-shielded, then it will show higher chemical shift. Okay, so since these protons are bonded to, these are directly connected to carbon, but in the neighboring in the neighbor of the carbon, it is bonded to an oxygen atom. So these protons are de-shielded, and hence they will have a higher ppm value. Okay, so this peak will correspond to HB, and this peak will correspond to HA. Okay, so I hope this example clears your concept about chemical shift. So yeah, 3 peaks will be obtained for methyl acetate in an NMR spectra. 1 peak will be obtained at 0 ppm for TMS, tetramethylsilane, and the other 2 peaks will be obtained for protons present in 2 different chemical environment. So these 2 protons are in different chemical environment, and hence these 2 will have 2 different peaks. So the proton which remains bonded to the carbonyl group or the COO group will have a higher de-shielding, and hence it will show a higher chemical shift. Now coming to the next question, that arrange the proton chemical shift of the following compounds in increasing order of their ppm values. We have 4 options, and in the 4 options you have 4 different compounds: CH4, CH3F, CH3OH, CH3Br, and you have to arrange their chemical shift in order of their ppm values. A moment. So has anyone solved this question? So just now we discussed an important concept, that the chemical shift of a compound will depend on the electronegativity of the surrounding. Chemical shift, what will it depend on? It depends upon several factors. One of the factor is that the chemical shift depends upon the electronegativity of the surrounding. Will depend upon the electronegativity of the surrounding nuclei, or it will depend upon the electronegativity of the surrounding atom. Okay. So you have to apply this concept for this question. So basically you have 4 different compounds. CH4. Second is what? CH3F. That is CH3OH. And fourth is CH3Br. There are 4 compounds, and you are recording the proton, the chemical shifts of the proton for these 4 compounds. So the chemical shift of these protons will depend on, so if of these protons will depend on what type of atom is present in their surrounding, whether it is oxygen or bromine or fluorine. Okay, so you know the electronegativity of these atoms. So as we know that in the periodic table, fluorine is the most electronegative atom, followed by oxygen, and then so out of these 4 different surrounding atoms, fluorine, oxygen, and bromine, the fluorine has the highest electronegativity, followed by oxygen and then bromine. Right. So as we said that chemical shift is directly proportional to what? Is directly proportional to the electronegativity of the surrounding atom. So the more the electronegativity, the higher will be the chemical shift. So now I hope you can arrange this in the order of their ppm values, parts per million. So since fluorine is the most electronegative atom, the CH3F will show the, if we record the proton, the chemical shift of proton of in CF or this compound CH3F, this will have a higher ppm, then followed by CH3OH, followed by CH3Br, and then CH4. Okay. So the higher the electronegativity of the surrounding atom, the higher the de-shielding effect, and hence higher will be the chemical shift. So the correct answer is option 4. CH3F will be greater than CH3OH, CH3Br, and then CH4. Okay. So the same thing is written over here. So chemical shift depends on the electronegativity of the surrounding atom, of the neighboring atom surrounding the proton. Okay. So it will depend on the electronegativity of the neighboring atom surrounding the proton. As fluorine has the highest electronegativity, it will cause maximum de-shielding of proton. Therefore, CH3F will have the highest chemical shift. Okay. So you can write another extra information you can note down is that the electronegativity of fluorine will be more than oxygen, will be more than. So this is the order of the electronegativity of the neighboring atoms. So since the chemical shift will be proportional to electronegativity, so the chemical shift will also have this order. Okay, I hope this question is clear. And now moving to the next question. So I have so in proton NMR spectroscopy, which of the following groups would typically appear at the lowest field? Lowest field means downfield, will appear downfield in the spectrum. So for this question, I have already given a hint. And this is the hint. I hope you this table this figure was also there in your lectures. So you need to have an idea about the different functional groups of which functional group show a higher chemical shift, which shows a lower chemical shift. So you do not need to memorize the chemical shift, but if you have a rough idea that which functional group shows a higher chemical shift and which shows a lower chemical shift, then you can solve these questions. So what will be the answer? The hint is already given. Someone try it out and tell me the answer. So this figure shows the proton H1 chemical shift ranges with reference to TMS. So the here starting from left to right, or you can say from right to left. From right to left, the ppm value is increasing. So it starts from 0 ppm. So 0 ppm is for TMS, and then each and then the proton will show depending on what is the functional group or what type of nuclei with which it is attached. It will show different chemical shift. So for example, this saturated allylic, what does this mean? So if the proton is attached to a saturated compound, for example H2C, then what will be its saturated means single bond. Okay, allylic means CH2 double bond CH, CH3. Okay, alcohol means this proton is surrounded by a functional group OH. Okay, so alcoholic, vinylic, and so as we can see in this table that if the proton is surrounded by an acidic functional group, or for example, so we are not so if we take the NMR, if we record the NMR spectra of carboxyl as of a compound which has a carboxyl group, then the proton which is attached to this carboxyl group will show the highest ppm, or it will show the have the highest chemical shift. Okay, so this is for aldehyde proton CHO. So this proton H, amide will mean NH, aromatic means anything you can consider benzene. So these protons, okay, CH2, CH2. Okay, so these protons. So this is a table which shows the uh, chemical shift of protons, protons which are present in different functional group. So always remember that the carboxyl acidic protons shows the highest chemical shift. Okay, so the correct answer is option D. Okay. So lowest field or highest ppm. So the question can be asked in different manner. Lowest field does only means that the lowest field means higher chemical shift, right? Lowest field means downfield and high. So all these are different terminologies, but the thing is the same. So moving to the next question, question number 9. A proton NMR spectra was recorded in a 400 megahertz spectrometer. To obtain the following data, what will be the corresponding chemical shift values? So we already solved this type of questions in the initially in question 1 or 2, these type of questions were there. So for different. So these are different compounds, and for these, the resonance frequencies are already given: 1486 Hertz for CCl4, CH3Br is 604 Hertz, CH3, CHO is 728 Hertz. Okay, now you have to basically convert these frequency into ppm. Okay. So here the chemical shift is reported in Hertz, and you have to, the question that is asked here is, that has been asked here is that you have to report this in terms of ppm for all these compounds. And one more thing to note here is that the spectrometer in which we are recording the frequencies is 400 megahertz. So this is the, so 400 megahertz is the frequency of the spectrometer. So we already discussed this question. So all of you try this question, and then we will take up this question, and we will see what is the answer for each of the 4 compounds. As it was discussed in the lecture also, so you can also think of ppm as hertz by megahertz. Okay, so parts per million. Per million means what? 10 to something divided by 10 to the power 6, right? So has anyone solved the first part of this question? That what would be? What will be the chemical shift of CCl4, calcium carbon tetrachloride, in ppm? So just now what we discussed was that 400 megahertz. What does this mean? 400 megahertz would mean that 1 ppm is equal to 400 hertz. Okay. Now the reason now this chemical shift is reported in hertz, and you have to convert it into ppm. So accordingly, or you can get the values. How much will this be? So this will be, sorry, ppm. This would be 3.715 ppm. Similarly, you can also You can also get the ppm values for these molecules. CH3Br, CH3CHO. So already the chemical shift has been reported in Hertz, and you can convert them into ppm value. Okay. So you have to apply the same concept that so what you have to do is basically you have to divide each of those resonance frequency with resonance frequency or this chemical shifts with 400 to get the value in ppm. Okay. So for B, this would be 604 by 400, and this would be 728 by 400. And for D, option D, so you can solve these and you can get the answers. Moving to the next question. This is also a similar question. A chemical shift of around 1.8 is seen in proton NMR spectrum on a 500 megahertz spectrometer. With respect to TMS, how far is the peak from TMS in hertz? So you apply the same concept and get the answer. So if anyone has solved this question, you can tell me the answer. So anyone?
ये A का with respect to TMS, the far is the peak from TMS in hertz is 900 hertz.
Okay. Okay. Good.
And for the
Good.
this
Good.
one,
Yeah.
800 into 1.2 into
Okay. So how did you get
144.
this? How did you solve the part A of this question?
144. See, the spectrum is recorded on the
So you can just multiply 1.8 by 500.
into 500.
Yeah. And so how much this will be?
900.
900, right? So on 800 megahertz instrument, what will be the chemical shift? So in 800 megahertz instrument, the chemical shift would be 1.8 into 800 hertz. That would be how
Same.
much? It will be same.
It will be the same. There is no change.
Okay. Yeah. So yeah. So can you explain why there will be no difference in chemical shift? So there, so for example, so the question is 1.8 ppm, right? So if you convert this 1.8 ppm into hertz, how much will you get? How much will this come? 1440. Okay. So so this is the frequency of this proton frequency of the proton on a 800 megahertz instrument. But here what is asked in this question? In this question, you have to see if the chemical shift. So for getting the chemical shift, what you have to do? So if you divide this 1440 by 800, this will be equal to how much? So as we know that the chemical shift is equal to nu minus nu naught by nu or nu of the spectrometer into 10 to the power 6. So if you divide this frequency by 800 hertz, this will be equal to how much? 1.8. So that is the basic concept of chemical shift. So we the chemical everything is reported in ppm because to remove so that we can remove the dependence on external magnetic field. So whether the spectra be recorded on 500 megahertz spectrometer or an 800 megahertz spectrometer, the chemical shift that we will see will not be different. So there will be no difference in chemical shift. So I hope you understood this concept. There will be no difference in chemical shift. Okay, so in this question, you have to comment whether there will be any difference in chemical shift. And so chemical shift, how we get? We divide this. If we divide this frequency by 800 hertz, then this will also be equal to 1.8 ppm, the same chemical shift that we were getting in on a 500 megahertz spectrometer. Okay. So calculate the difference will be 0. Okay, in chemical shift in hertz. So we have been told to calculate the difference in chemical shift in hertz. So in hertz, the chemical shift will be different, but in ppm, there will be no difference in. So when we report it in ppm, there will be no difference in chemical shift. Okay, so for 1440 hertz minus 900 hertz, this would be how much? 540 hertz. Okay. So So the this so this question I had given so that you can understand the basic concept of chemical shift. That the chemical shift will always be the same, whether for a particular nuclei, the chemical shift will be same if it is recorded in a 500 megahertz spectrometer or in a 800 megahertz spectrometer. Okay. So now moving to the next question. So how many non-equivalent hydrogen are there in the given molecule? So this is the molecule, and you have to determine the multiplicity of each kind of hydrogen in the given molecule. So these type of questions were discussed in the lecture. So if I would want everybody to try this question and tell me the answer. So anyone who knows the answer, you can unmute yourself and tell me. So how do you decide whether the proton is an equivalent or whether it is non-equivalent? how many peaks will you get? So we were discussing how many peaks we will get for different compounds. So you have to apply the same concept here. So non-equivalent, the term non-equivalent hydrogen means that these hydrogen will have different chemical shifts. They will show different ppm value in the NMR spectra. And if the protons are equivalent, then these protons will have the same chemical shift. There will be, we will for so if for example, be it three equivalent protons or four equivalent protons, for all these protons, we will have a single peak. And for non-equivalent protons in an NMR spectra, we will get different peaks. Okay. So I hope you understand the concept of equivalent hydrogen and non-equivalent hydrogen. So if non-equivalent hydrogen would mean that we will get different ppm values for these hydrogen. But if the protons are equivalent, then for all these protons, we will have a single peak. Okay. Now, depending on the number of protons that are present, that will determine whether the intensity of the peak will be, what will be the intensity of absorption of the peak. Okay. What will be the absorption of the peak, whether it will be this much or whether it will be this much. So what will be the intensity? That will depend on the number of equivalent protons. Okay. So if you see this compound, if you see this molecule, if you expand it and write it. So this carbon is what? This is sp3 hybrid. This is sp3 hybridized, and all these protons, these methyl protons that are attached to this carbon, and they have the same chemical environment, right? They have the same chemical environment. So if you imagine this. The structure of this molecule in three dimension, then you will understand that all these three, all these three methyl groups are in the same chemical environment. Okay, they will have since they are in the same chemical environment, all these protons are the same. Okay. Protons are the same, but if you consider these two protons, the protons which are present in this in CH2Br, CH2Br, these protons are present in the neighboring atom present to these protons is Br, bromine. So because of this bromine atom, there will be de-shielding, and hence so this will show a different chemical shift. It will have a different chemical shift. Okay. So so how many non-equivalent hydrogen are present in this molecule? So the answer is 2. So we have 2 non-equivalent hydrogen present in the molecule. So what are the 2 non-equivalent hydrogen? One hydrogen which is attached to the methyl group, and another hydrogen which is remains which is present in the CH2Br. Okay. And how do you determine the multiplicity of each kind of hydrogen in the given molecule? So what is multiplicity? This concept was discussed in great detail about spin-spin coupling and J coupling. So what does it mean? That the proton, the nuclei of the nuclei, one nuclei is affected by by its surrounding nuclei through electron or through bond. Okay, so that is called spin-spin coupling. So if they so this is a nuclei. This has a spin. This and this is surrounded by another nuclei. Okay, The influence of one nuclei on the other nuclei is called spin coupling. And how do you calculate the multiplicity? How do you calculate the multiplicity? Multiplicity of a proton is given by n plus 1. Okay, n plus 1. What is n over here? N is the number of neighboring protons. Number of neighboring protons. Neighboring protons or non-equivalent protons. Or so first we will consider this proton of methyl group. So this proton is surrounded by, so the neighboring, this is the CH3. So you have to this. So if you see this, so consider this figure. So this proton is attached to the carbon atom, and this carbon atom is bonded to this carbon atom. So this carbon atom, does it have any proton? This carbon atom does not have any proton, right? So you have to look for, so if for example you want to calculate the multiplicity of the methyl proton, then what you have to look? You have to look for the protons which is present in its surrounding atom. So how many protons are present in its surrounding atom, and whether it is equivalent proton or non-equivalent proton. So as you can see here, that this proton, methyl proton, is the neighboring atom of the methyl proton, that is carbon, that does not have any proton, that does not have any hydrogen atom. So since it does not have any hydrogen atom, so its multiplicity will be what? It will be singlet. So n will be 0, 0 plus 1, and this will be 1. So we will get a single peak for this methyl proton. Okay. And now if you see, now we will calculate the multiplicity of this proton, B. So let's name this B and let's name this C. If you calculate the multiplicity of B proton, then how many, what will be the multiplicity? So you look for the surrounding atom. Its surrounding atom is also carbon. Is also this carbon. This carbon does not have any proton. Okay. So if for this case also, the n is equal to 0. The n is equal to 0. So n is equal to 0. So here also we will get only one. The multiplicity will be 1, which means that it is singlet. 1 means singlet. And what will be the shift, chemical shift? Can anyone say? Where will be where will be H and where will HB in the NMR spectra? So which one will show a higher chemical shift? So HB. So HB will show a higher chemical shift because it is surrounded by the electronegative atom bromine. Okay. This is HB. This is HA. Okay. So remember this formula, that multiplicity is equal to n plus 1, and where n is what? N is the number of neighboring protons. M is the number of neighboring protons. Okay. So similar to that question, there is another question. So this is one word. Okay. Yeah. So how many non-equivalent hydrogen are there in the given molecule? So we will go one by one. So the first question is CH3, CH2, CH3. So how many non-equivalent hydrogen are present in this molecule? So when you are calculating the number of non-equivalent hydrogen, then you also have to look at the symmetry of the molecule. Symmetry of the molecule. So if you see the symmetry of the molecule, if you consider plane passing through the center of this molecule, then this is exactly this CH3 is exactly mirror image of the CH3 present on the right hand side. So this is symmetrical. So whenever it is symmetrical, this hydrogen is equivalent to this hydrogen. Okay. So all these hydrogen are equivalent hydrogen. And this CH2 will be, this will be different. This will be different from the so this is methylene proton. Methylene proton will be different from the methyl proton, and if we consider a symmetric axis passing through the center of the molecule, then these protons are all equivalent. So the number of non-equivalent hydrogen in this molecule will be 2. Okay. Number of the non-equivalent hydrogen in this molecule will be 2. So if the question is asked that how many signals will you get in an NMR spectra, you will get 2 signals. You will get 2 signals. And now what will be the multiplicity? What will be the multiplicity? Who can say? So for each A, the multiplicity will be, so multiplicity is n plus 1, and n is what? N is the number of non-equivalent hydrogen. Number of non-equivalent hydrogen. So there are 2 non-equivalent hydrogen. So n will be how much? N will be 2. And so the multiplicity will be 3. Okay. And now for this HB, if we want to calculate the multiplicity for this methylene proton, what will it be? So will it be 3 plus 1 or 6 plus 1? So what is so the formula for multiplicity is n plus 1. N is the number of non-equivalent protons. So since since this CH3, the proton, this protons and the proton which is present on the left and the right, this CH3 and this CH3 is equivalent. So the number of protons will be 3 and not 6. Okay. So we will get a triplet and a quartet. A quartet and a triplet. Okay. So how will the spectra look like? How will the spectra look like? So CH3 is highly shielded. So we will get its chemical shift near 0 ppm, and it will be a triplet. So it will be this one, and this one methylene proton. We will get a quartet, means this will be or not this. It will be just a second. In this, yeah. Okay, this will look like this. So this one will be higher, a little higher. So I hope you remember the Pascal's law. So based on this will be the center peaks will be higher than these 2 surrounding peaks. Okay. Now moving to question number B, Cl, CH2, CH2F. So CH2. Now these protons are this proton and this proton will be the same, because the surrounding and this proton HA and this proton has the same chemical environment, while this one will be different because the surrounding nuclei with respect to this proton B is fluorine. So the number of non-equivalent hydrogen will be 2 for this case. Now if we calculate the multiplicity of HA, it will be how much? It will be 3. That is a triplet, and B also we have 2 protons in the neighboring atom, so it will also be 3. So we will get 2 triplets in the NMR spectra. We'll get 2 triplets. Now considering so moving to the third one, see ethane. Ethane is CH3CH3. So ethane in ethane, so again you have to, if you consider the symmetry of the molecule, this if you pass a symmetric axis to the center of the molecule, then this symmetric axis exactly divides it into 2 halves, and so these protons are all equivalent. Okay, so all these protons are equivalent. So it will have, so all these protons are equivalent. So there will be 0 non-equivalent hydrogen. There will be 0 non-equivalent hydrogen, and hence the multiplicity will be 1. Multiplicity will be 1 for the for 12C. What about 12D? Do you expand it? This will make things clear. So these protons in its surrounding, it has a bromine atom, this proton, and this proton is surrounded by a chlorine atom. Okay, so these protons will be, and there is no symmetric axis in this compound. Okay, so these will have 3 non-equivalent hydrogen. Okay, so you are understood why this will have 3 non-equivalent proton, because this proton has bromine in its surrounding, and this HC has chlorine in its surrounding, and this is a methylene proton. So therefore we will have 3 non-equivalent hydrogen. 3 non-equivalent hydrogen, and you can apply the similarly you can apply the multiplicity formula for this carbon. The multiplicity will be what? It will be 2 plus 1, 3 for HA. For HB, will it be 2 plus 1 or 4 plus 1? It will be 4 plus 1, okay? Okay, so I hope this is clear. Now, similarly, you can solve these type of questions. So here, both these protons are equivalent. Okay, so there will be 0 non-equivalent protons, and the multiplicity will be 1. Okay, for B, what will be the multiplicity? How many non-equivalent protons? So this proton has chlorine in its surrounding, this proton has bromine in its surrounding, so there will be 2 equivalent protons, and the spin multiplicity will be 3. For C, now this is a case of geminal coupling. So in geminal coupling, what happens is that this proton has chlorine in its surrounding. This proton has chlorine in its surrounding, and this proton has bromine in its surrounding. So there will be two non-equivalent protons. So there will be 2 non-equivalent protons. And now in this case, what you have to do now, I had told that the multiplicity is given by n plus 1. N is the number of protons in the neighboring atom. number of non-equivalent protons in the neighboring atom. Okay, but here you see, if you see the neighboring atom of carbon of CH2, it is CClBr. So this carbon does not have any proton, but but in this case, this is a case of geminal coupling. You have to consider this proton, and so it will be its surrounding. This will be 1 plus 1 equal to 2, and for this proton, this will be, you have to consider this proton because this proton is in a different environment. This proton is near to bromine atom. This proton is near to chlorine atom. So for this proton, the multiplicity will be HB, the multiplicity will be 2, and for H also the multiplicity will be 2. So it will be a duplet. Okay, so we'll have two duplets. Now, moving to this 14th question. So how does NMR spectroscopy help in distinguishing cis 1,2-dimethyl cyclopropane, trans 1,2-dimethyl cyclopropane, and 1,1-dimethyl propane based on the number of signals? Now you can draw the formula for these compounds. So cis 1,2-dimethyl cyclopropane will look something like this. The trans 1,2-dimethyl cyclopropane will look something like this. This hydrogen. And 1,1-dimethyl propane will. Okay. Now, for these type of question, you have to consider the symmetric axis. So three compounds. Now, what you have to consider in this type of questions is that consider that this cyclopropane is lying in one plane. Okay, the cyclopropane is lying in one plane, and the CH3 groups and the hydrogen groups are lying above and below, lying below and above it. Okay, so how many protons will be there? Now here also you have to consider what, that there are two protons. One is lying above this plane and one is lying below the plane of this cyclopropane. And the third here also you have to consider the same thing, that one is lying above the plane, one is lying below the plane. And here you have to consider one more symmetric axis, that if a symmetric axis passes in this way through the center of the molecule, then what will happen? This proton will be equivalent, and this proton will also be equivalent. Okay. And this proton will be equivalent, CC. So we will have how many non-equivalent proton in this question? We will have 3 non-equivalent protons in this. Not 3, this will be 2. So basically, just a second. Yeah. So this. So then this symmetric axis passes through in this manner. This proton and the proton which is lying above the plane, proton lying below the plane will be same. So we will have 3 signals. Okay. We will have not 3 signals. We will have 2 signals in this case. Okay. Now in this case, this proton is has a surrounding so in its surrounding it has another proton. Okay. And in another side this is CH3. Now if you look at the proton which is present below the plane, this proton has CH3 on this side, and this proton is on another side. So these will be non-equivalent. Okay. See. Similarly, this proton will also be different. So there will be 4 signals in this case. Okay, but if you look at this one, cis 1,2 dimethyl cyclopropane, then considering this proton lying above and below the plane, this proton and this proton will be equivalent. This will be A, this will be A. Similarly, so you can consider a symmetric axis passing through the center. This will be the same, and these ones will also be the same. Okay. So here you have, how many signals will you have? Here you will have actually 4 signals. Okay. These ones will be different. So I would like you to think on this question. The answer is 4 signals, but why will it be 4 signals? Signals you have to consider, you have to think about this. You have to consider 3-dimensional arrangement of these protons, and we can again discuss this in the next class. Now there is moving to the next question, which of the following statements are correct? The most downfield shifted proton in CH2 double bond CH-CHO is the proton in the aldehyde group. Now this question, I had mentioned the table of chemical shift in one of the slides. So you can refer to the slides, and you can. So for this question, the first statement, we will look at the statements one by one. The first statement states that the most downfield shifted proton in CH2 double bond CH-CHO is the proton in the aldehyde group. Proton in the aldehyde group. So this is true. Okay. So if you see the figure that I had shown previously, that the proton, the aldehyde proton which is present in aldehyde has the highest downfield shift compared to the methyl this alkene, this CH2 double bond CH. In this proton and this proton, it will have the highest downfield shift. Hydrogen bonded proton and protons present in aromatic ring causes downfield shift in proton spectra. This is also correct because whenever the proton is hydrogen bonded, it will cause a higher downfield chemical shift. And in the aromatic ring, due to ring current, pi electron ring current, this was explained in the lecture. You can go through it if you do not remember. So the pi electron ring causes the downfield shift in case of aromatic ring, and the chemical shift of a proton. This is also correct statement. The third statement is the chemical shift of a proton will depend upon the chemical environment of its nuclei. So this is also correct. We have been discussing this since the very first, since the starting of this lecture, that the chemical shift of a proton depends upon the chemical environment of its nuclei. So all these statements are correct. Okay, option 4. Now, last question of this session is a molecule with molecular formula Ce3H7Cl produces 2 peak in the proton NMR spectra. How many peaks would a proton decoupled C13 spectrum of the molecule produce? Now, C3H7Cl. So the molecular formula is given. So C3H7Cl can have, what will be the structure? Can anyone say what will be the structure of this molecule? C3H7Cl. So it can have two structures, CH3, CH2, CH2, Cl. So this is one possibility. So if you see, there are 3, and how many protons? 3, 4, 5, 6, 7. And another formula, or the if you the organization, or what will be the other possibility? Other possibility is CH3, CHCl, CH3. Okay. So this formula can have either this structure or this structure. Now, which structure now? How will you determine which structure is present? This one or this one? So you have to if you read the question carefully, you will see that it is written that a molecule with molecular formula C3H7Cl produces two peaks. Okay, it produces two peaks. So structure, for this structure, how many peaks will be present? How many peaks will be present? So all these protons are non-equivalent, right? A, B, C. So all these protons are non-equivalent. So if this molecular formula, if this compound having the molecular formula has this structure, then there will be three peaks. Okay. While if the compound having this C3H7Cl has this formula, H3C, CH3, then how many peaks will be present? These two are equivalent, right? And this will be non-equivalent, so it will have two peaks. Okay, did you get it? So this will have two peaks. So the correct structure of the molecule with this formula would be this one, CH3, CHCl, CH3. As it is mentioned in the question that this molecule has two peaks in the proton NMR spectrum. Proton NMR spectrum. So this molecule, so this is the correct structure of the compound having this formula. And now if you now what you have been asked to find here is that how many peaks would a proton decoupled C13 spectra. So if you were recording the proton spectra, then you would be getting two peaks. But in the question you have been asked to find out that how many peaks you will get if you are recording the C13 spectra. So if it is a C13 spectra, so so in a C13, the C13 spectra, how many peaks will you get? So this carbon will be equivalent to this carbon. Okay. This carbon will be equivalent to this carbon because if you see this carbon, this has also one H and one Cl in its surrounding, and this carbon also has one H and one Cl in its surrounding. So these two carbon will be these two carbon will be equivalent, while this carbon will be non-equivalent because this has a chlorine in its surrounding. So yeah, in C13 spectra also we will get two peaks. Okay, C13 spectra also we will get two peaks. But if you had a compound, for example, this one CH3COCH3. So if the compound, so for example, if you have another compound, this is what? This is propanon, right? Propanon. So in this case, the number of proton peaks will be for this compound, if you record the H1 spectra, then you will get only one peak because this proton is equivalent to this proton. But if you record this is proton spectra, okay? This is proton spectra. So if you record the proton spectra, you will get only one peak. But if you record the C13 spectra, if you record a C13 spectra, then how many peaks will you get? Now you will get two peaks, okay? Because this carbonyl carbon will have a different chemical shape than this methyl carbon. So you will get two peaks. One is for the methyl carbon and one is for the carbonyl carbon, okay? So you have to read the question and then you have to answer that what is asked in the question, whether it is asking you C13 spectra or whether it is asking you the number of peaks in proton spectra. So for this question, the correct answer is 2. Okay. I hope this is clear. Now, this is the last question. So number of proton peaks for the following compound would be. So if you so you can solve these questions. They are all the same. You can expand it and write. This is just a second. So O. This is you can just write it in this manner. So these will have CH2 groups. Double bond CH2. Expand it and write. This will be CH2. Now, now this is a very symmetrical molecule, right? If you if you look at it carefully, then it is a symmetrical molecule. So these protons are equivalent. These protons are equivalent. OCH3, the protons which are connected, protons which are part of this OCH3, they are equivalent, and these protons are also equivalent. Okay. H. So you will get two peaks. Okay. So there will be two peaks. So one is for the methyl proton, which is bonded to an oxygen atom, and one is for the methyl for the aromatic protons. Okay, for the aromatic protons. So this is a very symmetrical molecule. So all the protons in this CH3 is equivalent to protons of this CH3, and the aromatic protons will also be equivalent. So the correct answer is option 2. So that was all for this week, and I hope you could understand all the questions that I discussed today. If you have any further questions, we will take it up in the next class. And I would, if anyone has missed, you can go through this video. And if you have any doubts, we will discuss it in the next session. I hope the session was useful to you. Okay. Thank you.